Mice pie. Mice never tasted so delicious.
Today we are going to talk about the height matching problem. So let's see what the problem is. Now suppose each of three men at a party throws his hat into the center of the room. The hats are firstly mixed up, and then each man randomly selects a hat. What is the probability that none of these three men selects his own hat? That is a problem. We have these three men throw his hat into the center of the room, they mixed up, and then each man randomly select one hat. What is the probability that none of these three men select his own hat? What is the problem? Can you solve this problem? Pause this video if you want to give it a try. Please like this video and subscribe our channel to get more interesting math problems. Now, in order to solve this problem, we're going to introduce some preliminary rules of probability. Now, the first one is so-called the complement rule of probability. So what is that? It basically states the following. If A is an event and AC raised to C is a complement of this event A, then the probability of AC equals 1 minus the probability of A. Here is the example. Now, for instance, the probability it is not going to rain tomorrow is 1 minus the probability that it's going to rain tomorrow. Another example here is the probability that COVID-19 will not last for another year is 1 minus the probability that it will last for at least another year. So this is the complement rule of probability. Another rule is so-called the product rule. Here, let A and B be any two events with probability A is greater than 0, then the probability of the intersection equals probability A times the conditional probability of B given that A has occurred. Now, for instance, here's the example. If you randomly select two cards from a stand deck of playing cards without replacement, what is the probability that first is a heart, denoted as H1, and second is a diamond, denoted as D2? So in order to find this probability of one event and another event, though we can use the product rule. So probability of H1 intersect probability D2 equals, well, using the product rule, probability of H1 times probability conditional probability of D2, given that the first is a heart. So it can be easily calculated the probability for the first to be a heart, that's 13 over 52, because there are 13 hearts among a deck of cards. Times, now this conditional probability of D2 given that H1 is 13 over 52 minus 1, because this after the first draw of a heart. Now we have to be careful. This drawing is without replacement. Now after the first draw of a heart, there are 51 cards left, among which there are 13 diamonds. So that is why this conditional probability is 13 over 52 minus 1. And you can find this probability is 0.064. Now this is the product rule. Another rule is the so-called the inclusion and exclusion identity. Now here is for three events. Now let E1, E2, E3 be any three events, then the probability of the union of these three events equals given here. All right, so there is a generalization of this inclusion and exclusion identity, which we listed here, but we're not going to use it in this problem. Now, we're ready to solve this problem. Okay, three men at a party, throws his head into the center of the room. The heads are firstly mixed up, and then each man randomly select a head. What is the probability that none of these three men select his own head? How to solve this problem? All right, now let's consider this. Firstly, we're going to define some events. Now, the general idea of solving this problem is, now, firstly, find the probability of the complementary event. So what is the complementary event that none of these three men select his hand? So the complementary event is going to be at least one man selects his own hand. Okay. Second, now the probability that none of them selects his own is just 1 minus the probability that at least one man selects his own head. Now, this is based on the complementary rule of probability, right? So if we can find the probability that at least one man selects his own head, all right, then this probability none of them selects his own head is just 1 minus the probability that at least one man selects his head. So this is using the complementary rule of probability. Now, question is, how to find the probability that at least one man selects his own head? Well, we define our events as here that EI denotes the events that the ith man selects his own head. I here is 1, 2, 3, so we have E1, E2, and E3. Then this probability of the union, E1, union E2, well, here should be E2, and union E3 is the probability that at least one man selects his own head. Here, I'm sorry, here it should be E1, union E2, union E3. Then, using the inclusion and exclusion rule, we have the probability of E1, union E2, union E3 equals, well, this formula here. All right, inside this formula, we see that there are probability of EIs and the probability of the intersection of a pair of events. So E1 intersect E2, E1 intersect E3, and finally E2 intersect E3. And lastly, the intersection of all these three events. So we basically need to find out all these probabilities. The probability of EI, probability of the intersection of a pair of events, and the probability the intersection of all these three events. How to find this? Now let's consider this. Now, probability of EI is 1 over 3. This is very simple because anyone is selecting any of the three heads. So for each of them, that's 1 over 3. Probability of EI is 1 over 3. Second, the intersection, probability of the intersection of a pair of events is simply 1 over 6. Why is this true? Is we're using the product rule. Here, probability of EI intersect EJ, all right, it equals this product rule probability of EI times the conditional probability that probability EJ given EI has occurred. So what is the probability EI? That's 1/3. We already found it in step 1. Now, given, all right, using the product rule here, the second term, all right, this conditional probability is 1/2. Now, why it is 1/2? So here is the reason is that the conditional probability that the jth man selects his own head, given that the ith man has selected his own head. Okay, so for instance, if one man has already selected his own head, there is just 2 heads remaining. So among these 2, he's randomly selected one of them for the jth man, so the probability he gets his own head is just 1 out of 2, 1 over 2. So that is why the conditional probability is 1/2. So therefore, this probability of the intersection equals 1/3 times 1/2 is 1/6 using the product rule. Finally, this probability of the intersection of all these three events, we are going to use the generalized product rule. So it equals, you can see we view E1 intersect E2 as one event, all right, and then use the product rule. So it equals the probability of E1 intersect E2 times the probability of E3 given that E1 and E2 has occurred. So we already found in step 2, this probability of the intersection is 1/6. Then what is the conditional probability? Now this conditional probability is 1. All right, that is to say the third man selects his own heads, given that the first two men get their own heads. Well, this is of course 1, right? So because there are 3 heads, the first two men get his own head, the head remaining just belongs to the third man. So the third man gets his own head after, given the first two men got their own head, is just 1. It's absolutely sure. So this conditional probability is just 1. So we have the probability of the intersection of all these 3 events is 1/6. Then we are ready to solve this problem. Okay, just plugging all these values into the formula. Here we go. The probability of E1 union E2 union E3 equals, plugging all these values, we found is 2/3. All right, 2/3. Then what is the probability that none of these 3 men select his own head? All right, using the complementary rule. All right, so we found the following. None of them selects his own head equals 1 minus the probability at least one man selects his head. So which is 1 minus the probability of the union, all right, E1 union E2 union E3, which we already found. It's 2/3. So it equals 1 minus 2/3, which is 1/3. Now therefore, we got the probability that none of these 3 men selects his own head is 1/3. All right, very good. Now let's consider generalization of this problem and see if you can solve this. At a party, n men take off their hats. The hats were then mixed up, and each man randomly selects one. We say a match occurs if a man selects his own hat. What is the probability that no matches? What is the probability of exactly k matches? Can you solve this generalization of this problem? All right, leave a comment below, and I look forward to seeing you in the next episode. Thank you.